One question that has come up a few times is, when is a square matrix invertible? This is especially a question that has come up in the context of this sort of linear equation, right? This sort of linear equation always has a unique solution exactly when this matrix A is invertible, so we'd like to have a good way of knowing when a matrix is invertible. Unfortunately, at the moment, the only way we have of knowing if a matrix is invertible is actually row reducing the matrix and seeing if it reduces to the identity. So maybe there's a better way. Unfortunately, since we don't have a better way, if we want to know if some general matrix is invertible, at the moment, really all we can do is row reduce it and see if it's possible to row reduce it to the identity. So let's see if we can row reduce this to the identity. This is going to be a little tricky because we have variables here in our entries instead of particular numbers, but let's see what we can do. Now, one tricky bit about row reducing is the row operations that you do to row reduce actually depend on what the entries in the matrix are. So for example, if this top left entry were 0, the first thing we would do is swap the first two rows. If this top left entry is 1, then we wouldn't swap the rows. So it's a little tricky to know how to row reduce this when it's all variables, but let's assume that nothing goes wrong as we do this row reduction. So when I say assume nothing goes wrong, let's assume that this entry isn't 0, and let's just see what happens. So maybe the first thing that we would do is get ourselves set up to use the top left entry to zero out the bottom left entry. So one nice way to do that is to multiply the first row by A21 and multiply the second row by A11. Right? If both of these were 0, that would cause a problem, but let's assume that that doesn't happen. So when we do these row operations, we get, let's see, in the first row we get A11 times A21, and then here we get, let's see, A12 times A21, and then in the second row we get A11 A21 and A11 A22. Okay, so then the next row operation, I guess, would be to use the top left to zero out the bottom left. So we're going to do row 2 minus row 1. This gives us A11, A21, and then A12 times A21. And now when we do row 2 minus row 1, this bottom left entry zeroes out. And then in the bottom right, we have A11 times A22 minus A12 times A21. Okay, now as long as this lower right entry isn't 0, then we can use the bottom right entry to zero out the entry above it, and then we'll almost have the identity, right? We'll need to adjust the sizes of these entries by multiplying the rows by some constants, but as long as these aren't 0, we can make that happen and we'll be able to reduce to the identity. So what we're seeing here is that it looks like A is invertible if and only if, so exactly when, this weird combination A11 A22 minus A12 A21 is not equal to 0. Okay, so this combination of entries in a 2 by 2 matrix it's special. It's a function of all of the entries in the matrix, and it's a very special function because when it's non-zero, you have an invertible matrix. So we're going to call this, we're going to give it a name. We're going to call it det A, and this is short for determinant. Okay, now to have an invertible matrix, your matrix has to be square, right? This one was 2 by 2. So this is the determinant for a 2 by 2 square matrix, but I mean, what about other sizes? Generalizing the determinant formula formula to larger matrices is actually a bit of a pain, so it's sort of a multi-step process, so buckle up. Once we have a formula written down, we'll look at some examples of actually calculating the determinant just to get used to how the formula works. So, the multi-step process for defining the determinant. The first step is, it's defined inductively, right? We're going to start defining the determinant on a size 1 by 1 matrix, and then we will use that to define it on size 2 by 2, and then use that to define it on size 3 by 3, and so on. So for a 1 by 1 matrix, which is just a scalar, the determinant of the matrix is just that scalar. So it's just the single entry in the matrix. So now what we're going to do is assume that we've defined assume we want to define a matrix for size n by, or define the determinant for size n by n, and assume we've defined it for smaller sizes, right? So what we'll do is, right, since we've defined it for 1 by 1, the next size would be 2 by 2. So we'll use the 1 by 1 definition to define 2 by 2. And then we'll use the 2 by 2 definition to define determinant for 3 by 3, and so on. And, you know, when that infinite process is done, you have a formula for the determinant of any size. All right, so suppose we've defined the determinant for smaller sizes, sizes up to n minus 1 by n minus 1. Then the determinant for the n by n square matrix is defined like this. First, we're going to come up with just an abbreviation. So this is minor a sub ij. This is the determinant of the matrix obtained by deleting the ith row and the jth column. So A is some big matrix. You take the ith row, the jth column, and you just cross those out. When you do that, what you're left with, right, you've deleted one row and one column. Well, now you're left with an n minus 1 matrix, or an n minus 1 by n minus 1 matrix, right? And we've assumed that we've defined the determinant for this smaller size of square matrix. So the ijth minor a sub ij, is just the determinant of this matrix that you get by deleting the ith row and jth column. The cofactor in position ij, so the ijth cofactor of A, you just take that ijth minor, the determinant of that smaller matrix, and you multiply it by either a plus or a minus, depending on I and j. So you add I and j, and you raise minus 1 to that power. I know this seems like a crazy thing to do, but it works. So now that we have this cofactor defined, the determinant of size n by n, what we're going to do is sum up. So we're going to go across this first, across this first row. We're going to take the entry in each position times the cofactor for that position, and just add them up across the first row. So this definition is a bit wild. So let's look at some examples just to see how it works. We'll start out with a couple 2 by 2 examples. Remember, for 2 by 2, we actually already had a definition. It was A11, A22 minus A21, A12. But let's use this cofactor thing to calculate the determinant of this matrix. So determinant A is, so remember, it's a sum from j equals 1 to n, which is 2 in this case, a1j times the cofactor of A in position 1j. Okay, so when j is 1, we get a11 times the cofactor of A in position 1, 1, plus a1, 2 times the cofactor of A in position 1, 2. Okay, so a11, that's 3. Now this cofactor, remember, it's minus 1 to the ij times the minor of A in position ij. So minus 1 to the, I plus j. So we're in position 1, 1. So 1 plus 1 is 2. Minus 1 to the second power is 1. Okay, now we do the cofactor, or now we multiply by the ij minors, so the 1, 1 minors. So we go to our matrix, we cross out the first column and the first row. That leaves us with just the matrix minus 4. We take the determinant of that, which is going to be minus 4. Okay, plus a1, 2, which is minus 1. Then we get minus 1 to a power that's the sum of these two positions. So 1 plus 2 is 3, so minus 1 cubed, times the determinant of the 1, 2 minor. So cross out the first row and the first column. We're left just with this bottom left corner. So that's so we need the determinant of the matrix, the 1, 1 matrix 1. Okay. So this gives us, let's see, minus 3 times 1 times this determinant. Determinant of minus 4 is just minus 4. So 3 times minus 4, that's minus 12. Plus, and then minus 1 times another minus 1 times a plus 1. So that's plus 1. So this is minus 11. Okay. Now, this formula really is the same thing as the one we had before. So there's a11, that's right here, times a22. There's a22, right? This determinant of minus 4, that's really a22. And this minus 1 was squared, so, minus 1 squared, it doesn't show up here because it's just times 1. Okay, plus this minus 1 cubed, that's that minus sign in the middle. This minus 1 was supposed to be a minus 2, right? This should be this position right here. So this should be a minus 2, and that's going to change the result. That's going to make this 2, and so this should be minus 10, I guess. Okay. So this minus 2 is this a12, and then determinant of 1, well, that's a21. So you see, we are getting all the same entries of the matrix in the same places. It's just the way we're getting them is insanely complicated for no apparent reason, right? So for this 2 by 2, the 2 by 2 determinant is simple enough to write down sort of explicitly, so expanding it in terms of cofactors is a little bit pointless, honestly. So usually when you get down to a 2 by 2 matrix, you'll just use this formula. And one more thing to point out about this formula is it's the product of these two with the plus, right? A11, A21, A22. And then the product of the other diagonal, but with a minus. Okay, so that's usually the shortcut that I'll use. So if we use that trick, this sort of cross trick where the going down and right is positive and down and left is negative, we'll get, so 3 times negative 4 minus negative 2 times 1. So this is negative 12 plus 2, so that's 10. You see, the weird cofactor expansion worked. Okay, so let's calculate the determinant of this matrix. Okay, so let's use the easy 2 by 2 formula. So it's 8 times 6 minus, and then we do the other diagonal, so negative 3 times negative 16. So these pluses are going to cancel. So 8 times 6 is 48 minus, and then 3 times 16 is also 48, and that's 0. Remember, we said that a matrix, at least for our 2 by 2 case, a matrix should be invertible when its determinant is non-zero. Well, this determinant is 0, so that means this matrix should be non-invertible. But look, that's the case because the columns of this matrix are linearly dependent. The columns of this matrix are multiples of each other. And we know if the columns are linearly dependent, then the matrix can't be invertible because it won't row reduce to the identity. All right, so that's 2 by 2. Let's try a bigger example just to see how this works. Let's do 3 by 3. Okay, so now this way of expressing the determinant in terms of cofactors and minors, so this is how you have to write it down if you're expressing the determinant for all sizes. For a particular size, though, there's sort of a nice shortcut. So we're going across the first row, so we're going to start out with a plus. And our first entry is 1. Then we need to multiply that by the determinant of, right, now imagine crossing out the first row and first column. We get these 4 entries in the bottom right. So 2, 4, 5, 3. Okay. Now for the next entry along, we aren't changing what row we're on, so we're still on I equals 1, but j is changing from 1 to 2 because we're going from column 1 to column 2. So the power on our minus 1 increases by 1, so this plus turns into a minus. Okay? And we'll see as we go across the first row, every step we take, the sign just changes. So it's plus, minus, plus. Okay, so minus, and now we take this entry, 2, times the determinant of, and then we cross out the column that we're on and the row that we're on, and we get sort of these four entries here. So 3, 4, minus 2, 3. Okay, now the next step along the first row, it was a plus before, was a minus on the last one, so now it's a plus. And then we have the entry in this position, which is minus 1, times the determinant of, and then we cross out the row and the column that we're on, and we're left with the 4 entries in the bottom left. So 3, 2, minus 2, 5. Okay, now for each of these determinants, these are 2 by 2 determinants, so we can use this cross trick to calculate each of these individual determinants. So let's see, 6 minus 20, so I'm sorry, 6 minus 20, so negative 14, right? Yeah, minus 2 times, so 9 plus 8, careful, because our second part of the cross is negative, but then there's a minus 2, so it's actually plus, so 9 plus 8, 17, and then plus minus 1 times, so minus 1 times, and then 15 plus 4 is 19. Okay, so minus 14, minus 34, minus 19. Okay, and then we have some arithmetic to do, so I don't know, 14, maybe it's not worth doing, but I feel obligated. 8 plus 9, 7, carry a 1, so 6, negative 67. This is negative 67, I think, if I did the arithmetic right. Okay, so that's for 3 by 3. Let's do 4 by 4. Now, 4 by 4 examples in general are going to be a huge pain because as you go across the first row, you're going to get 4 terms, and each term is going to have a 3 by 3 determinant, right? But each 3 by 3 determinant has 3 terms, each with a 2 by 2 determinant. So you just get lots and lots of terms, right? The calculation for a determinant gets very big very quickly as the size of the matrix grows. Fortunately for this particular matrix, there are lots of zeros. So a lot of the terms that we write down will have zeros in front of them, so we'll just get zeros from those parts. Okay, so determinant of A is, so now from this first position we get a 0 times some determinant of some big, right, this 3 by 3 in the lower right, but we won't have to calculate this determinant because it's being multiplied by 0. Okay, so the first term had a plus, so the next term is going to have a minus, and the entry here is 1 times the determinant of. Now, since we have a 1 here, we don't get to just ignore the stuff coming from this determinant. We have to write down what it is. So imagine deleting this row and this column. We get minus 1, 0, 1, 0, 1, 0, 1, 1, 1. Okay, now there was a minus, so next one is a plus. Third entry here is 0, so 0 times some determinant. But again, since it's being multiplied by 0, we don't have to worry about what this determinant produces. And then, let's see, minus, our last entry across the top is 0, again times some determinant, but is being multiplied by 0, so it doesn't matter. Okay, so we just get minus 1 times this determinant. And it's a 3 by 3 determinant, so we have to go across the first row. Minus 1, right, this top left entry, minus 1 times the determinant of the 2 by 2 in the lower right, 1, 0, 1, 1. Oh, okay. Minus 0 times, well, 0 times some determinant, but it's 0, so who cares what the determinant is, plus, and now we're in this third position, 1 times the determinant of the lower left 2 by 2 here, so 0, 1, 1, 1. I'm using round brackets for some reason. Okay. All right, so we have minus 1 times this determinant is 1, minus 0 plus 1 times, and then this determinant is minus 1. Okay, so we get minus 1, so minus 2 times another minus 1 is plus 2. All right, so the determinant of this whole thing is 2. You can see that since no matter what the size is, the determinant, writing out the determinant across the first row, it always gives you determinants of a smaller size. So, in turn, you would then express these smaller determinants in terms of determinants of a yet smaller size, until eventually you get down to 2 by 2 determinants, in which case you can just calculate them directly.